Bird's-eye view 3D object detection is a crucial multi-view technique for autonomous driving systems. Recently, plenty of works are proposed, following a similar paradigm consisting of three essential components, i.e., camera feature extraction, BEV feature construction, and task heads. Among the three components, BEV feature construction is BEV-specific compared with 2D tasks. Existing methods aggregate the multi-view camera features to the flattened grid in order to construct the BEV feature. However, flattening the BEV space along the height dimension fails to emphasize the informative features of different heights. For example, the barrier is located at a low height while the truck is located at a high height. In this paper, we propose a novel method named BEV Slice Attention Network for exploiting the intrinsic characteristics of different heights. Instead of flattening the BEV space, we first sample along the height dimension to build the global and local BEV slices. Then, the features of BEV slices are aggregated from the camera features and merged by the attention mechanism. Finally, we fuse the merged local and global BEV features by a transformer to generate the final feature map for task heads. The purpose of local BEV slices is to emphasize informative heights. In order to find them, we further propose a LiDAR-guided sampling strategy to leverage the statistical distribution of LiDAR to determine the heights of local slices. Compared with uniform sampling, LiDAR-guided sampling can determine more informative heights. We conduct detailed experiments to demonstrate the effectiveness of BEV-SAN. Code will be released. Object detection is an essential computer vision task, which has wide applications in security, robotics, autonomous driving, etc. The bird's-eye view is a unified representation of the surrounding scene and is suitable for autonomous driving tasks. Although the model architectures of those methods are different, they commonly follow a similar paradigm consisting of three essential components including camera feature extraction, BEV feature extraction, and task heads. Among the three components, BEV feature construction is BEV-specific compared with 2D tasks. Existing methods for BEV feature extraction flatten the BEV space along the height dimension, which fails to exploit the benefit of different object classes located at different heights. BEV-SAN samples along the height dimension to build global and local BEV slices and aggregates the features from multi-view cameras. The local slices emphasize informative heights, and a height attention mechanism is used to fuse the global and local slices. The paper also proposes a LiDAR-guided sampling strategy to determine the optimal heights of local slices. The method is evaluated through experiments and found to be effective in accurately detecting 3D objects in BEV space and determining optimal height ranges for informative BEV perception. The proposed method has potential applications in map segmentation and planning tasks. The method offers a significant contribution to the field of BEV 3D object detection and has the potential for future research and development. Here is the pipeline of the proposed SAN method. Our method follows the pipeline of existing methods, which consist of three components: camera feature extraction, BEV feature construction, and task heads. To be more specific, given an input multi-view images, we adopt a shared backbone model to extract the feature. We also predict the depth distribution map for each input image. Then we project the camera features to viewing FrustView and construct the flattened BEV feature with the proposed Slice Attention module. In Slice Attention module, we construct the BEV feature based on the global and local slices. We use a two-stage fusion strategy to merge the features of global and local slices for task heads. We first evaluate our method on NU scenes val set. The baseline methods are BEV-DET and BEV-depth. We report the results of BEV-depth under different height ranges, and the default height range of BEV-DET and BEV-depth is. We show the qualitative results of the baselines and our method. As can be seen from Figure 6, the proposed SAN improves the performance of 3D object detection. In this figure, we compare the results of SAN and BEV-depth. As can be seen from Tab 2, our method can improve the baseline method by 0.03 in NDS, and all the evaluation metrics are also improved. To further evaluate our method, we conduct the experiments with CBGS strategy, which will take much longer training time. As can be seen from Tab 3, our method can still improve performance even with the CBGS strategy. We conduct this experiment based on ResNet 50 in consideration of computation cost. Since the motivation of our method is to handle different object classes with different heights. Therefore, we show the results of different object classes in tab 4. We compare the map of the proposed SAN and baseline methods. For the results without CBGS strategy, SAN outperforms the baseline BEV depth in each object class. The performance gain of the traffic cone even reaches 0.038. For the results with CBGS, the SAN also shows significant improvement. For example, our method improves the baseline BEV depth by 0.032 in bicycles and 0.023 in traffic cones. These results show that our method gives different attention to objects with different shapes. In this section, we report the computational cost of SAN. As shown in tab 8, our method introduces additional computational and storage costs to the baseline methods. To be more specific, when the backbone is ResNet 101, our method introduces 41 MB storage cost and 27% slower than the BEV depth baseline. The most time-consuming step is building the features of global and local slices. However, this is because our current implementation simply repeats the LSS operations. More careful engineering optimization can help to reduce the computational cost of SAN, which will be our future work. More detail can be found on paper. Thanks.